So let's begin our study of electrodynamics. We're going to begin by briefly looking at charge conduction in conductors, and that's going to lead to discussing Ohm's law, looking at the Jude's law of conductivity, which is a classical approach, and we'll just briefly, qualitatively at least, talk about the extension of Jude's law using quantum mechanics to do the conductivity. Well, here are a few equations that partially at least we're familiar with. These are so-called empirical equations because they really rely on observations without theory. But basically what it says is that the polarization or the magnetization of materials depends on the strength of the field that's producing them. And in this case it's the E field, and here it's the H field. And you recall this chi was called the susceptibility, either electric or magnetic. If we look at the conduction process, then we have this current density, which is proportional to the E field applied, and this constant here is the conductivity. This equation is basically Ohm's law, and we'll see how that works. 1 over the conductivity is the resistivity of a material. Basically, as you increase the resistivity for a given E field, the current density drops. So here's the parameters then. J is the current density, sigma is the conductivity, and rho is the resistivity, and of course E is the electric field in the conductor. So here are the units for rho and for sigma, and you start by just taking the units of the components of the equation and put in those units. So for example, J is amps per square meter. Collect these in terms that you would have, for example, voltmeters over amperes, and here voltmeters seconds over coulombs when you express amperes in coulombs per second. And you just flip this to get the units of sigma. So that's what you see here. Here's some values of sigma for metals, and so if you have a very high value of sigma, then it conducts current very easily. If you have lower values, then you would consider it a more resistive material. Remember, you take the reciprocal to get the resistivity. So let's see which one has basically the highest sigma. It looks like it's this one right here, so for metallic calcium. I'm surprised because normally we think of gold and aluminum as being superior conductors. The units of the conductivity have also been called Siemens per meter. Siemens was a German scientist, and you may know him in terms of loudspeakers because of the company that makes loudspeakers with his name. We said E inside a conductor, which would be different from zero. Well, you recall that in electrostatics we stressed frequently that E was equal to zero inside conductors. And so charges would move until the E field inside would be zero. Now we state that if we can maintain E different from zero inside, the current will be non-zero and continue to flow as long as we can maintain that E field. So how do we do it? How do we get E different from zero inside the conductor? Well, the answer is you have some source of current, some source of voltage, which you can maintain. And so things like batteries, power supplies, solar cells, windmills, what have you, that can supply a potential difference and maintain it, then as long as you can maintain it, you can have an E field inside the conductor. Well, let's take a case of a cylindrical conductor. So it's shown here. It has a length L and a cross-section A, shown here. And it has two potentials, V sub A, V sub B, at the two ends of the cylinder. And it's made of a material that has a constant conductivity, sigma. First we want to find the E field inside the conductor, and we want to find J in terms of the parameters given. We're going to assume that J is proportional to E, just as we did for Ohm's law, and then find the current in terms of the parameters and change this into the engineering form of Ohm's law, which you are familiar with. Okay, so the first thing we want to do is find the electric field, E, inside the conductor. And so we begin by making sure we understand that there's a potential difference between the two ends. which would be equal to V sub B minus V sub A. Now realize almost all the time one of these is zero. It doesn't have to be, but this would be just zero potential, and then the other potential would be some different potential which would give us a non-zero delta V. The resulting electric field inside the conductor, if we assume that it's uniform, is related to that difference of potential. So here it is again, and we set that equal to, remember that we can find the difference of potential by integrating the E field along some path between the two ends. So here, if we have, for example, the end A and the end B, if we integrate E from one end to the other along some path inside the conductor, then we will get E times L because we assumed that the E field is uniform. We can go through our steps of taking E outside. dl is parallel to E, and we end up with this equation here. Just solve for the magnitude of E, and you can see that it's delta V over L. As long as the cylinder has some resistance, we can have a hope of maintaining that delta V and have E different than zero. The second part is to assume that J is proportional to E and find J. We have the current density, J, and by Ohm's law we set that equal to sigma times E. And all we have to do is substitute E in, which we just found. So the current density will be equal to sigma delta V over L. So you can see that if you have a way of keeping this under control so that you can maintain delta V, then you're going to have a current density. Well, finding I in terms of this equation up here is very simple because we just multiply by the area. So we end up with the current density times A, which would give you the current. So the last part is to change this into the form that you're used to using. We first of all identify R as being the length of the system divided by sigma A. So we can just solve for R and we get rho L over A, because sigma is 1 over rho. So these two equations are equivalent to each other. Okay, so then if you plug those into I, so then you have I, which is equal to J times A. Rearrange all of this, you'll end up with, here's our resistance, R, so you have delta V over R, which is the normal version of Ohm's law. Just to remind you, resistivity is a property of a given material. So if you choose copper, steel, water, what have you, that gives you the resistivity depending upon the structure and so on of that material. Resistance is a property of a particular specific object. And what we're talking about is the shape. For example, a car key, a piece of wire, and it's dependent upon the material because you have the rho dependence of R. Here's R again. It's rho times L divided by A. And so you can see where A and L are properties of the geometry of the object, and rho, of course, is dependent upon what kind of material it is. If we take I equals V over R, just remember that V is the potential difference between the ends of the conductor, and you have I proportional to V. Well, that's a linear dependence, and you're familiar with materials that are said to be ohmic if this curve is a straight line. And so if we plot I versus V, the slope is 1 over R. So if you have R very large, then the slope is small. For a given voltage, you have less current. The other way around, if R is very small, then it doesn't take very much voltage to get lots of current, so the slope changes accordingly. Now there's a lot of interesting materials that are non-ohmic, and I show you here one in which there's curvature. The slope is not constant. In this particular case, as you have increase in voltage, the slope is getting higher and higher because R is decreasing. So that gives you this shape here. And like I say, there's lots of materials that have this type of curve. Well, we've derived the continuity equation several times, but let's go over it quickly. What you're considering here is you have basically a volume and has a surface S and a volume tau. It contains a certain amount of charge Q, and the density of that charge is rho. R is the vector that points to the little positions, little d taus in the material. We've called that R prime before, but let's just call it R. So how are the current and current density related? Well, if you have this S, the current that's either going in or out of the surface is equal to the integral of J dot ds. The current is equal to dq dt. So if a dq of charge enters or leaves the surface in a time delta t, you take that ratio and that gives you the current. Now, conservation of charge says that if we integrate the current density over the volume, that will give us the Q inside. Suppose you have current flowing out for a long time, say, then what's going to happen is the Q inside is going to decrease, and so what happens, of course, is the current density inside is decreasing. That's where this equation comes from. It's conservation of charge. If we take this charge as a function of time and take the derivative of it, that gives us the current. We just take the derivative of the integral right here and place the differential inside the integrand, so we have d rho dt times the volume, and integrating that over the volume. Realize that if I is positive, so if you have current flowing out, then the total charge inside, and we consider that positive charge, will be less than 0. So we're going to put the minus sign here, so we just rewrite dq dt now with the minus sign. And don't forget that we've already shown that this current is equal to this surface integral of the current density, using the divergence theorem to get a volume integral. And so we take the left-hand side to be this expression here, and we take this expression and turn it into a divergence. Since this holds for any volume, we can take the two integrands and set them equal. And so what we have here is that the divergence of J is equal to minus d rho dt. And this is the continuity equation. It assumes no sources or sinks contained in tau. If current goes in, rho goes up. If current flows out, rho goes down. We know that moving electric charges is what gives rise to electric current. Let's suppose we have in a current flow n discrete charges per unit volume. We'll say each is of charge q and it's moving with velocity v. Realize what this is some average drift velocity in the conductor. Let's take this box, which we form in the following way. We have a area S, and we'll put that on both ends. We're going to take the length of the box to depend on this velocity. So in other words, if we start the flow at t equals 0 and let it go t at a given velocity, we're going to take the length of the box to just be v times t. If we started at t equals 0 empty and allowed it to fill up, then if we freeze time here, we can calculate how many charge carriers are inside the box. And what it will be is that we'll call it capital N. That's going to be equal to the density of charge in numbers. So this is the number per unit volume times the volume, and that will give us the number of particles that have passed through S. And so if we take the volume to be the volume of this box, so we've filled up the box during this time, then it will be x times S, where x is given by Vt. The charge Q contained in the box is just equal to the charge of each carrier times capital N. So I restate that here. Q is the charge per particle. Now if these are electrons, it could be the charge on the electron. So rewriting this, this is Q, the total charge, is equal to Q times N times X times S. This is just repeating what we've had here, but now let's look at the rate. And this is the rate at which charge fills the box, and therefore the rate at which charge passes through S. It's given by just taking the derivative of capital Q right here, and we've got the left-hand side, so we can take the derivative of it. And you'll notice that the only thing that could depend on time is the x. We place the derivative in front of x, and so we have q little n dx dt times s. Well, this is the velocity. So putting that in then, the current in or out of the box, depending on the sign, is equal to q n v times s. So this is the current flowing through either this S or this S, because we assume that there is no source or sink, so everything that enters comes out. If we take S small, J is going to be constant over that surface. We don't have to do any integrals. And so we have I divided by S, that's equal to the current density. Taking our current to be this expression here, divide by capital S, and we have J equaling Qn times the velocity. Think of it this way. NQ is basically the charge per unit volume times the velocity, which will give us the current density. Just to be careful about all of this, we first assumed up here that the current was normal to the surface, but that may not be the case. So we really have to consider the orientation of the vectors. If we have S actually ds and J, they may not be parallel, so we have to consider then taking the dot product, which gives us the component of J parallel to the ds vector. The other way to say it's the perpendicular J perpendicular to the surface S. If we integrate that over the surface, this is a variable that depends on the position, so J may depend on where it's hitting the surface S. So the way I show it here, for this particular point right here, J is pointing in this direction, ds is normal to the surface, so we take the dot product, and what we get is the normal component of J times the magnitude of ds. If we're going to take the whole S, we'll then get the total current that's flowing through S. So the integrand is evaluated over all points on S. You might notice that when we take something and integrate it over the surface, especially when there's flow, we call this the flux. So current is in fact the flux of current density. Look at this product Q times N. Remember, this is a number density, so the units are 1 over volume. And so if you take Q times that, that will be in fact charge divided by volume. And that's the charge density in the flow. Now warning, we use rhos and sigmas all over the place. So be very careful to determine what kind of rho we're talking about. So this is the charge density, the volume density. We can write then that the vector J in all its glory is the current density, which depends on position and could depend on time, and the velocity of the charge at a given position and a given time. So rewriting the whole expression here then, this is equal to this expression here. All we've done is put in all the variables. And like I say, normally we just write it like this. So rho times V dotted into ds, so you'll notice that v dot ds is what determines the magnitude of this integrand. J can be made from different charge carriers. So for example, you may have electrons, you may have holes, you may have plus and minus ions. In solutions, for example, you're likely to have ions. And in plasmas, you're very likely to have ions. In fact, I don't think you can have a plasma without ions. Both have electrons. If you have a semiconductor, normally it contains both electrons and holes as charge carriers. One will go one way, the other will go the other way when you apply a voltage. Well, let's talk about the Jude model. This is a fairly interesting model. It was developed back in the early 1900s. The idea is to try to apply kinetic theory of gases to electrons in a solid. And the idea is that you have these electrons represented by these blue symbols, and the ions of the lattice are shown as these red circles. If you have collisions with these lattice ions, then you will change the direction of the velocity and make it harder for charge to move through the material. And so what Jude was saying is that if we use the kinetic theory of gases to describe this process, we might be able to quantitatively examine that. This is at Molecular Expressions, which has a number of E&M applets. What you see here is a light bulb filament, and this is the current which is going to deliver the current to the filament. Right now there's zero current, but if I put a little bit of current, you can see these balls bouncing across the screen, and you can see that they're going in both directions. Now, I don't know if you can see it or not, but if you watch carefully, the electrons that get scattered back turn around and go back this way. They may undergo collisions, but I think you can see if you watch carefully this process, and the reason is because the E field is pushing them along. Of course, if these are electrons, the E field is in this direction. Okay, so let's increase the current like this, and you can see all you're doing is increasing the number of electrons. So the density of electrons is going up as you increase the current, and so then this just keeps going up. Now in principle, the velocity does not change. Okay, remember I is equal to rho times V. So that's why if we have constant velocity, to get more current you just increase the density. And so then you get ridiculous and you have this very high density. You can go to this web page and play with it if you wish. So let's go back to the expressions that we're interested in. So we have the basic model. One of the things that's wrong with this model is it gets the wrong drift velocity, but it's going to get us Ohm's law. The result is shown right here. The current density is going to be a set of constants here times the E field, and if you remember, this was the conductivity. So this is Ohm's law right here. What are the constants? N is again the number density of the charge, Q is the charge per particle, and tau is a time between collisions. So up here, if you looked on the average, how long it takes to collide with the ions, that would be tau on the average. And of course mass is the mass of the particle. A more modern picture is that there's basically several carrier scattering mechanisms. One actually is if you have impurities. And if you have ionized impurities in the material, that will lead to scattering. The other important one is phonon scattering, and we'll discuss that in just a minute. And then finally, scattering from defects. These are really the major reasons that electrons, for example, have difficulty getting through the material. Some other scattering centers are dealt with defects such as the vacancies in the lattice, interstitials, and what are called dislocations, sometimes referred to as line defects. This is a sketch of a line defect, an edge dislocation, and what you see here is an extra plane inserted between these two here. It only extends down to here, and so you notice that the lattice beforehand, which is perfect, has this other plane inserted, and that's called a dislocation. Charge trying to get by there will be scattered because the electric fields are distorted because of this. One of the major scattering mechanisms is phonons, and this really can only be explained in terms of quantum mechanics. So what you do is you consider the vibrational motion of the lattice in terms of a quantized system that is described by waves. So remember, in electromagnetic waves you can describe energy transfer in terms of particles, namely photons. Lattice vibration energy transfer is attributed to a quasi-particle called phonons. So that's where the overlap between photons and phonons, the names are similar. Real particles, like electrons for example, can scatter off phonons and thereby gaining or losing energy. These collisions result in slowing down the flow of charge through the material. One thing that this explains is that if you increase the temperature, you generate more phonons. So therefore, the resistance of the material goes up, and it's predicted from this phonon model that the resistivity of a material with temperature will be linear. And what you see here is the resistivity of copper. Jude, on the other hand, predicts that that would go up as t to the 1/2. The good news is Jude predicted that it would go up. Actually, people knew that, but he was trying to get the right dependencies. The bad news is he got the wrong exponent. Theory that was developed in the 30s and 40s got this result very nicely from quantum mechanics. So let's do an example. Let's find the drift velocity, or V average, for a conductor, let's say copper, and we're going to assume 1 electron per copper atom. And so we'll have this conductor be a wire that's 1 millimeter in diameter and carrying a current of 1 ampere. We first want to find the density of free charge. This would be the free electrons in the copper. And so that's going to be equal to rho sub q, where here now we're talking about charge density. So this is charge per unit volume. To do that, we basically take the number density of copper atoms, because that's going to give us 1 electron per copper atom here, and we change that to a charge density by using the charge on the electron. And so what we end up with is 1.4 times 10 to the 4th coulombs per cubic centimeter. So just one more time. This is 1 electron per copper atom. We know the charge density right here. We can find that by taking the number of copper atoms per unit volume and multiplying by the charge on the electron. And so that gives us this quantity here. Now we can calculate the V average or V drift from the relationship between J and the velocity, where the multiplier is the charge density. So if we define current density as we know it is, it's the current divided by the cross section. We're given that this is 1 ampere and the diameter is 1 millimeter, so we can get the cross-sectional area. If we then solve J equals rho V for the velocity, then we have J here and we divide by the charge density. If we take the area to be pi s squared, where s is the radius of the wire, then we can put in the charge density, which we calculated for copper, do the arithmetic, and we end up with this quantity here. So this says that the drift velocity is 10 to the minus 2 centimeters per second, and if you change that to another unit, that's 30 centimeters per hour. As I show here, that's really slow. This is snail's pace. How can this be? Well, you've got this wire. Okay, so here's the wire, and we have charge going in and charge coming out. Velocity, average velocity through this wire is this very small amount. Realize this all came out of conserving charge, and so if you look at the amount of charge going in per unit time, it's huge, because this quantity here is so large. So even though it's a very small velocity, you still maintain the current by just having this very large density of charge, and therefore lots of charge is entering and leaving the wire. Next time we're going to discuss another few concepts of conduction and talk about some applications.